morning, everybody. Well, it's morning as I'm recording this. It'll probably be afternoon as you're watching it. We are working today on an introduction to scientific notation. Okay. Scientific notation is exactly what it sounds like. It's based in science. We use it more there. And it's just a notation. It doesn't change the value of any numbers. It's a way of writing a number that's complicated to understand or complicated to read. Okay. So in the notes, the typed notes, it says some numbers are so large or so small that they're difficult to write. I would add or understand. We start counting the zeros and trying to figure out if it's a million or a billion. And you guys found that when we were working with exponents. Okay, so as we're working with exponents, you're finding that these numbers are getting really, really large. This part didn't photocopy so great, so I'm going to read it to you, and then we're going to put a little notation next to it. The first factor is greater or equal to 1 and less than 10. Okay, so the first factor needs to be between 1 and 10. Okay. And then the exponent is an integer. That means it can be positive or negative, and we will see what that means. Okay. So standard form, the normal way I would write a number, 692,000. Scientific notation, 6.92. Okay. Sorry, the lights in the classroom. 6.92 times 10 to the fifth power. Okay. Which means that the decimal here is then 10 to the fifth power more than this unit right here. So this is between 1 and 10, this number, times 10 to the fifth power, 10 with 5 zeros, okay, which gives us this number if you multiply them together. It's just a way of shortening it and being able to make comparisons with really big numbers or really tiny numbers. So let's look, okay? For this one, okay, 213 million. Instead, they wrote 2.13, a number between 1 and 10 to the eighth power. That means they moved from the end of the number 8 decimal places. Okay? If I'm given the number, then I know that I move out that number of decimal places. Okay? It can also be used with small decimal values. Okay? So if I have a negative exponent, I now have a small decimal amount. Okay, positive exponent, large number or large value. Negative exponent, small, what we would normally call a fractional value. Okay. So let's try a couple. Okay, let's use 809,007. You know what? Let's not use that one. Taking it from the curriculum is just not a great choice. Let's use 87,000, and let's use 0. Okay, So we're writing down these two. In standard form, okay, and that's where they are. They're in standard form. The decimal is here at the end of the number. If I want to make 87,000 or 87 a number between 1 and 10, I'm going to write 8.7. Sorry about the lights again. Sorry, that's the reality of the classroom. So between 1 and 10, there's my number. But where did my decimal move in order to get that value? 1, 2, 3, 4 spaces. So it's times 10 to the fourth power. Now, how can I prove that's true? Well, 10 to the fourth power is right here, right? 8.7, if I multiply those, I get the same number. So this is your proof. This is why that works. Okay. Now, if I have a decimal value, I already have an existing decimal. Now I'm moving my decimal to the right. 1, 2, 3, 4, 5 spaces. I get a number that's between 1 and 10. Okay. Times, and remember I moved 5 spaces, 10 to the negative fifth power. Okay. And if I wanted to prove that, I could write this as 5 7/10 times 1, 2, 3, 4, 5. There's my proof. That's its value. Okay, so that's where the concept comes from. The doing it is just moving around a decimal. But I want you to understand that what you're actually doing is multiplying or dividing by powers of 10. Okay, which is increasing this value as appropriate. Okay. So let's look at a couple more examples. 1 light year. Okay. And you guys know that this is actually a measure of distance, not a measure of time. So it's how far the light can go in a year. Be right back. Okay, how far the light can go in a year. Miles per year. Now, for our purposes, I'm going to round this a little bit, okay? So it's about okay. That's still a ridiculously hard number to say, to work with. So in scientific notation, I could write this as a number between 1 and 10 times, well, how many place values did I move? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that's in a normal way it would be used. Okay, another normal way it would be used is, okay, diameter of silt. I'm measuring water quality. Okay, and I have this number. Okay, that's a lot less than a meter. Okay, tens, hundreds, thousands, 10,000s, 100,000s. We're getting into teeny tiny infinitesimal measurements. Instead, I could write 3.9, a number between 1 and 10, times 2, 3, 4, 5, 6. 10 to the negative 6 power. Okay? So all we're doing is showing a way of comparing. Now, when on earth would I use this? Well, let's say I'm looking at that diameter of silt. 1 second. Take that back. Let's say I'm looking at a bank account. That's more fun. Okay? Now, if I don't write the commas, this gets really weird to figure out. But I could write 1.0 times 10 to the what power? 1, 2, 3, 4, 5, 6, 7, 8, 9. Or 1.0, 1, 2, 3, 4, 5, 6, 7, 8. I automatically know that this one's larger without having to count. So that can be a very quick reference point for scientists. That is why we're doing this. So that's your introduction. We're just going to convert some numbers for the first day or two, and then we'll do some work comparing different values. Have a great day. Thanks, guys.